Hello, today I'll walk you through the implementation of write follows read session guarantee, and the information will be based on this excellent article which is present on the screen. It's very clear, easy to read, and I definitely recommend it. My name is Ivan Fedyanin, I am software architect, and on this channel I am doing series of videos about distributed systems. Let's start with short recap of write follows read guarantee. To see more thorough explanation, just see my other video about client-centric consistency models. Here we have a distributed storage system containing 3 servers, and there is some kind of replication happens between them, but we don't really care which kind of replication. For us, it's important that the system will be eventually consistent, meaning that all writes will eventually be distributed across all servers. First, client called Alice starts a session depicted here with a red circle, and in scope of that session she makes the read R1, which returns the result of the write which was already present on that server, write W1. And then, having seen that write, Alice issues write request in scope of the same session and writes W2 on that server. And basically, write follows read session guarantee requires that everyone who would see the results of write W2 also would see the results of write W1. This restriction is not applied only to one session. It applies to all possible reads from all possible clients. For example, here we have a client named Bob who makes the read from server 2, and the server 2 contains both W1 and W2. So when Bob makes the read, he sees the results of both writes, and thus write follows read guarantee is satisfied because when Bob sees W2, it also sees W1. When Bob makes the read from server 3, it contains only W1. But the condition of write follows read is also satisfied because there is no any restriction about W1. This restriction is only about that when we see W2, we must have W1. But W1 could be seen without any other conditions. The simplest implementation of write follows read would be just using sticky session, and we could have some component called session manager which will be responsible for redirecting clients' requests always to the same server, and if all reads and all writes are made from the same server, then there will be no anomalies related to distributed systems, and the guarantee will be automatically satisfied. And it's very simple, and sometimes it's okay to use such guarantee, but it has drawbacks, and specifically those drawbacks are related to failover process. If one server happen to die, then client will not be able to make next request to this server, and the client has to switch to another server. And at this moment of switching, the guarantee might be lost. Let's try to solve that problem by making a system which literally ensures that definition is satisfied. And the definition of write follows read guarantee basically says that if clients makes the read and then makes the write, then whoever sees the result of client's write must also see the results of all writes relevant to the first read of that client. In other words, it means that this write made by client is applied on every server on the top of the same state which was seen by client when he made the read before doing the write. To make such system which satisfies the definition, we need to track all writes, and we will start by assigning unique identifier across all servers called with to each write. Also, let's introduce a component called session manager, which will sit in the middle between client and server, and it will be responsible for proxying client requests to the servers, which will satisfy the write follows read guarantee. There are several requirements to the servers which are not very strict and could be reasonably imposed on any eventually consistent system. So first one is that server, apart from the storage of the data, it must store all widths of all writes in some separate storage. Secondly, it needs to keep track of all relevant writes for each data item which is stored in its data storage. Thirdly, server has to provide an interface by which a client could check if some specific set of writes is present on this server. And finally, there is a requirement that all writes must be accepted and propagated between servers only in their write order. Session manager's responsibility will be keeping track of all widths of all writes which are relevant to all reads made within the session. And when write request will come from client, session manager will have to iterate through all servers and check if that server contains all widths which are present in session manager's read set. And if it's true, then such server is eligible to make the write. If it's not true, then it should check another server. Let's see how it works together. We'll start with some writes, and in the initial state, there is no data in the servers, and the read set of session manager is empty. And first, the client wants to make first write. For now, we did not do any reads, so we don't need to do anything special to satisfy write follows read guarantee. When client makes the first write, it's sent by session manager to server 1. Server 1 assigns width 1 to this write, adds this x equals 1 to its data storage, and adds to its relevant write storage width 1, because width 1 will be relevant for that value x, which is stored there. And then it returns a response to session manager, and it's forwarded back to client. When client wants to make the second write, it's similarly forwarded by the session manager to server 1. It's assigned width 2, and notice how width 2 replaces width 1 in relevant write set of the server, because we override that variable and previous write does not matter now. And then the response is returned to session manager and it's proxied back to client. And the third time, client now wants to make a write which is not override x, but it increments it. So it's a bit different because we can't replace previous value, but we need to know previous value. It again comes to server 1. Now server 1, it adds this write ID to the relevant writes, because from width through itself, we could not say what is the value of x. We also need previous value. And then it's a response to the session manager and the client. To make further illustration, we need to make some replication, and we assume that server 1 has replicated first two writes to server 2, and now server 2 is one write behind of the server 1. At this point, having this state as an initial, we can illustrate write follows read guarantee. First, client makes the read. This read is forwarded to server 1, and as a result, the value of x is returned to session manager, and also all relevant writes which led to this state are also returned to the session manager, and session manager stores them in its read set. Next, write happens. And during the write, it's now responsibility of the session manager to find such server which would satisfy write follows read guarantee. So first it checks server 2 and asks if server 2 contains all widths which are stored in read set of the server. And server 2 responds negatively because it's behind. Then it checks server 1, and server 1 responds positively. And thus session manager decides that server 1 is eligible for making the write which would satisfy our guarantee of write follows read. So the write is done to specifically server 1 and the result is returned to client. As you can see, this method works, and we've just seen how the write was prevented, which is not follows read, but this method had major drawbacks. First one is that servers and session manager has to keep very huge sets of widths, and also session manager on each write request has to send this huge set of width to the servers. In practice, it's not really feasible to do because those sets will grow with time in any real system, and at some point we will not be just able to use this method at all. So it's very good for illustrative purposes because it clearly shows how we can achieve this guarantee according to its definition, but in reality we will use another method. The actual industrial implementation of write follows read guarantee is based on version vectors. The main idea is that all potentially infinite set of widths on the servers and on the session manager are compacted into small version vector containing only number of elements equal to the number of servers. Each server will have its own clock. Those clocks could be any type of clocks, like real-time clock, Lampert clock, or simply counters. And the only requirement to the clock is that the value of the clock for each subsequent write should be bigger than for any previous writes. So every server will contain a small vector containing all values of clocks of all other servers. So, for example, if we have 3 servers in our system, then each server will have a vector of 3 elements. And in its vector, server will be responsible for only one element corresponding to its own clock. Here it's depicted with red. And when replication happens together with the data, those version vectors are also replicated and synchronized. To make it work, we need to define 2 operations on those version vectors. First, we will say that version vector v1 dominates version vector v2 in case every element of vector 1 is more or equal to the corresponding element of vector 2. We need this operation of domination to understand if server is behind or ahead of another server. And another operation which we need to define is merge. When 2 version vectors are merged, for each server in that vector we choose maximum value. We need merge operation to update version vectors during replication between servers and to update read or write vector in the session manager when it receives version vector from the server. Now, when we know some basics, let's see how it works together, and for now we will be interested only in what happens within the servers, taking client out of our consideration. Initially, clocks of both servers are zeros, and their version vectors are empty or zeros as well. And we have a set of writes which are coming to the servers in the specific order and applied one by one. When first write x equals 1 is coming to the first server, its clock are incremented, its version vector is updated, and the write is stored in the data plane of that server. The very similar situation happens with the second and third write. Next, we have 2 writes which are coming to the second server, and again version vectors are updated, clock are incremented. And now we ended up in the state when we have 2 servers in different state. We have some writes in one server and some writes in another server. And simply by comparing the version vectors together, we could see that one server is behind of another and the second server is behind the first one. Now let's assume that replication happened and all writes from server 1 are applied to the server 2 together with the update of version vectors. And now by looking at version vectors, we could see that now server 2 dominates server 1, meaning that it's ahead. And it could be set only by comparing small version vectors. And then we have opposite replication, and now version vectors are exactly equal, and we see that both servers are in the same state. So summarizing this all into the algorithm, we can say that to make the read, session manager can choose any server, but when it receives the response, it should merge the version vector which came from the server into its own read set. And when making the write, session manager has to iterate through all servers and choose the one which version vector dominates its read set. And in that case, write follows read guarantee will be satisfied. Let's see how it works for writes. So for now, we didn't do any reads yet, so we can choose whatever server we want to make the write. So first client makes the first write, and session managers forwards it to server 2. Server 2 makes several things under the hood. It increments its clock, it updates version vector, and just stores this data, and it responds to the session manager that the write was successful, which is just being forwarded to client. When client makes another write, it goes through the same steps, and in the end, version vector is updated and the clock value is 2 on the server 2. And the third write is processed very similarly, and in the end we have 3 writes in the server 2. It is reflected in its clock and version vector, and no writes in server 1. And now for our illustrative purposes, so let's assume that we have partial replication and first 2 writes replicated from server 2 to server 1. And it's also reflected in their version vectors, and by looking at their version vectors, we could say which server is behind. Now let's use this state in which we ended up or carefully prepared to illustrate how exactly write follows read would work. So client issues read request, which is forwarded to server 2, which is our most up-to-date server, and together with the response of the value x, server 2 provides also its version vector. This version vector is stored by the session manager in its read vector, and now during the write, session manager has to ensure that it makes the write to the specific server which has the version vector which dominates its read set. So first it checks if server 1 has the needed version vector, and the response is negative because we know that it's behind by 1 write. So it iterates and makes the check with server 2. Server 2 responds that yes, I have all the writes you need, and the session manager just decides to use server 2 to make the write, and the write is made, and the result is returned to client. So as you see, we just have prevented the violation of the guarantee by comparing version vectors of the server with the read vector of the session manager. This algorithm could be optimized even further. First of all, what if session managers tries to use sticky session approach and if possible use always the same replica for reads and writes? And in that case, we will save all those comparisons of version vectors and iterations through the servers. And it would work, and we will not have any anomalies. And in case of one server goes down and we need to perform failover, at this point, client could apply this strategy to find proper server which will satisfy this version vector's condition. So version vector of that server needs to dominate read set of client. And to make the failover even faster, client could cache those values of the version vectors of the servers. The difference between the first solution with only sticky session without this clever algorithm is that now we will not lose that guarantee during failover because we have an option to choose specific server. And in previous implementation, when we had just sticky session, we didn't have what we could do. So we have just seen how to effectively implement write follows read guarantee based on top of eventually consistent system using version vectors. For this, we have introduced session manager, a component which is responsible for forwarding requests from client to server and ensuring that write follows read guarantee is satisfied. It's doing this by keeping version vectors of the server from which it makes reads into its read vector. And on each write, it ensures that it writes to the server which version vector dominates its read vector. And each server, additionally, must keep only small vector with number of elements equals to the number of servers. And it's much more effective than the straightforward approach. Then we have seen that even this algorithm could be optimized and it could be combined with sticky session algorithm to make it even faster. I also recommend my other video to get a wider concept on the consistency models. So I have a separate video on client-centric consistency, which goes through all of them and covers use cases, more strict definition, and so on. And also I have a video about consistency in general with consistency continuum and linear reusability, sequential consistency, FIFO consistency, causal consistency, and eventual consistency explained. And also, if you are interested in the implementation of other session guarantees, then just refer to the videos on my channel, because eventually I'll make a recording about all session guarantees and their implementation. Also, I would be very pleased if you could subscribe on my channel, and see you next time. Bye.